Hi, welcome back to the lecture series on major theory with course code MMTC 202. Now we will going to discuss this section, the Lebesgue integral. So in this section, we'll first discuss upper functions. We'll first discuss upper functions. Okay. Upper functions. We know that the definition of step function. A step function. If phi is a step function, let phi be a step function. Let phi be a step function. Step function with standard representation. With standard representation. With standard representation. This phi is equal to summation I runs from 1 to n ai into characteristic function of ai, where these ai's are disjoint and where ai intersection aj is the empty set for I not equal to j, and the measure of these sets ai is finite for all I. So that's the standard representation of step function. The integral, the integral of a step function phi is defined by, it's already discussed actually, is defined by integral of phi is equal to summation I runs from 1 to n ai into mu star of a I. And we know that this integral is independent of this representation. Okay. Now, in future, we shall denote this integral by integral of phi I of phi by integral of phi. So from now, the integral I of phi will be denoted by integral phi d. Okay, so that is integral phi d mu is equal to summation I runs from 1 to n ai into mu star of ai. So that's the integral of step function. Okay. We have some properties. These properties of step function. That's the first theorem. First theorem. The collection of all step functions under pointwise operation. The collection of all step function is the collection of all step function is under pointwise operation is a function space okay, is a is a function space is a function space and also in algebra and algebra. Okay. Algebra, you know, by algebra we mean that it's a ring as well as a vector space, and it has more properties that club these two operations, multiplication and the multiplication of a ring and the addition of a vector space. Okay. So proof. So it's an algebra that's simple there, because we know that if I just find psi are still functional, then their product component-wise productive. Component-wise means that if we have two functions phi and psi, they are still functional. Then we define their sum is phi plus psi of x equal to phi x plus psi x. That's the addition, and the product phi psi of x is equal to, it's not the composite, it's a component wise product actually, phi x, because we cannot define composition here, phi x into psi x. And third operation, that's for these two operations, with respect to these two operations, it will form a ring. Okay, and we have scalar multiplication, alpha phi x is equal to alpha times phi of x. So this addition and this scalar multiplication will make this collection of all step functions a vector space. So it is a ring as well as vector space, and it is one more properties, that is this one, phi times psi plus say any other step function, say chi. Okay, it's equal to phi psi plus phi chi. So that's one more property, and therefore it's actually an algebra. So these are the properties of algebra actually here. So the collection of all step function is form an algebra. It's also a function space now, because if phi is a step function and the phi has this representation, I runs from 1 to n, ai characteristic function of ai, and then this phi plus is again, it's also a step function, it's equal to summation I runs from 1 to n. This is the maximum of ai 0, ai comma 0 into characteristic function of ai. It is again a step function. So therefore the collection of step functions is an algebra, and also a function space, and also because it is one this property also, no? And also a function space. Okay. Similar, this phi minus is also a step function. Okay. So whenever phi is a step function, phi plus is a step function, phi minus is a step function. So that means it's a function space. Okay. So next we define this upper functions. Okay, upper functions. Next we define upper functions. Upper functions. Upper function. A function f from x to x is mu is a fixed measure space throughout a function f from x to r is called an upper function. Is called an upper is called an upper function, is called an upper function if there exists a sequence phi n of step functions, if there exists a sequence phi n of step functions such that it will satisfy the following two properties, such that the first property is this file should increase to f. So that means this file is an increasing sequence and its limit is f almost everywhere. And the second property is the limit of integral of file is finite. Okay, so these are the properties of the upper function. A function f from x to r, a function f from x to r is called an upper function if there exists a sequence phi n of step functions such that this sequence increases to f. That means this is an increasing sequence and its limit must be equal to the function f, and the limit of this integral of phi n, this should be for, because this integral is already defined. Okay, integral of phi is already defined, so we take the limit of it, and if this limit is finite, then we say this f is an upper function. F is an upper function, and this sequence for this function, because this sequence exists for this function, this is for this function f actually, this is called the generating sequence for f. Okay, the sequence phi n is referred to as a generating sequence. Is referred to as a generating sequence for f. There may be more than one generating sequence for f. Okay, but whenever we have such a sequence for this f, then that sequence is called the generating sequence for f, and this f is called an upper function. Okay, so generating sequence has these two properties for this f. This phi should increase to f, and the limit of the integral of phi should be finite. Okay, so that's the definition of generating sequence for f, and the definition of this called the definition of upper function. Okay, now you can see this every upper function. That's the first way of following properties. Some properties. The first properties. Okay. First one is every upper function is Lebesgue measurable. Every upper function is Lebesgue measurable. This is simple because if f is an upper function, then there is a sequence phi n of step functions such that phi increases to f almost everywhere. Since we know that every step function is measurable, and f is the limit of that sequence, so therefore f is measurable. So every upper function is Lebesgue measurable. And second property, this every step function is an upper function, is an upper function. That's again simple. So if phi is a step function, then we define a sequence phi n, which is equal to phi itself for all n greater or equal to 1. Then this sequence is increasing sequence because it is phi 1 less or equal to phi 2 less, because each phi is equal to phi. So that means this is an increasing sequence, and then this phi n, it's an increasing sequence, and its limit is equal to 5. And one more thing, that this limit and approach to infinity integral of phi n, because each phi n is equal to 5, though it is just integral of 5. But phi is a step function, and integral of a step function is always finite, so this is finite. This is finite. So if phi is a step function, then we take the sequence of step functions as phi is equal to 5 for all n greater or equal to 1. And then you can easily verify that this phi is an increasing sequence, and limit of phi is equal to 5 because it's a constant sequence. Each phi is equal to 5. Okay, and the limit and approach to infinity integral of phi is equal to integral of phi, which is finite. So this phi, it's a step function. It has a generating sequence phi, which is phi itself or each other. So hence every every step function is is an upper function. Okay, every step function is an upper function. Now, one more thing that I want to mention here, which we have already discussed in the previous lectures. In the previous lecture on step functions, if we have two sequences, phi n and psi of step functions, such that limit of phi n increases to f, some function f, and psi n also increases to f. If we have two sequence of step functions such that phi n increases to f and psi n increases to f, then limit of integral of phi n is equal to limit of integral of. This is already discussed on the lecture on step functions. Okay, this one. If we have two sequences of step functions such that both sequences will increase to the same limit function f, then the limit of integral of phi n is same as the limit of integral of psi n. This is already discussed. Now, from this, we have following observation here. So let phi be a step function. Let f be an upper function. Let f be an upper function. Let f be an upper. So now next we want to define the integral of upper function actually. So let f be an upper function, and phi n be its generating sequence. Be it is generating sequence. Then we have this phi n. It increases to f almost everywhere, and the limit of integral of phi n is finite. Now let psi n be another sequence of step functions. Let psi n be another sequence of step functions. Sequence of step functions. Let psi n be another sequence of step functions such that psi n increases to f, such that psi n increases to f almost everywhere. So we have two sequence of step functions. One is phi n, such that phi n increases to f, and second is psi n, such that psi n increases to f. Then using this one, if we have two sequences, then limit of phi n, then limit of integral of phi n is same as limit of integral of psi n. So this is finite because this limit is finite, as phi n is a generating sequence. So thus this psi n is also a generating sequence because it has two properties. One which is already given, psi n increased to f, and second which we have obtained from this actually. Yeah, okay, this one. So therefore psi n is also a generating sequence. Therefore this psi n is also a generating sequence for f. And not only this, and the integrals are same. Integral of phi n is equal to integral of limit, not the integral, but the limit of this integral. Okay, so these limits are same. Both are finite. Okay. So therefore, we have definition. Actually, now this f, this upper function, is independent of the sequence phi n now. So if you have if you have say n number of sequences, then this limit is always same. So therefore, this will give the following definition. Okay, so we have following definition now. Following definition. Let f be an upper function. We define now integral of f actually. Let f be an upper function. And let phi n be its generating sequence, and phi n be its generating sequence. It's generating. Let phi n be its generating sequence. Then the integral of f is defined by integral of f d mu is equal to, that's the obvious way to define it, because this f increases to phi and integral of limit of phi is finite. Okay, so this is the integral of f. Okay, this is the definition of the integral of step function. So it is independent of the choice of the generating sequence. Okay, that's already discussed. Also, moreover, if f is equal to g almost everywhere, and f is an upper function, f is upper function and equal to g almost everywhere, and f is an upper function, then g is also an upper function. Then g is also an upper function. Not only this, their integrals are same. Integral of f d mu is equal to integral of g d because both are same generating sequence actually. So the limit of the integral of phi n, if phi n is a generating sequence of f, then this phi n is also a generating sequence for g. So that means the integral of f, which is equal to limit of integral of phi, it is same as the limit of the integral of g, because the phi n is the generating sequence for g also. So both the integrals are equal actually. So now we have a theorem which proves there's some linear problem, not the exactly linear property, because it's not closed with respect to scalar multiplication. This integral actually, these upper functions, it's not closed with respect to scalar multiplication. So, that we'll discuss in the future. Okay. For upper functions f and g, for upper functions f and g, the following hold. First part is f plus g. G is an upper function. Sum of two upper functions is an upper function. F plus g is an upper function. And the integral of f plus g is equal to integral of f plus integral of g. Second one, alpha f is an upper function where alpha is positive, not for every scalar. That's why it's not vector space actually. This is not closed with respect to scalar multiplication. Alpha f is an upper function where this alpha is greater or equal. It's not true for each alpha. Minus times negative times upper function need not be an upper function, but positive number times upper function is again an upper function. And this integral of alpha f is equal to alpha times integral of f. Alpha times integral of f. Third property is the join of two upper functions is an upper function and the meet of f join g and f meet g are upper functions. Upper functions. So it's actually a function space, but not in algebra because it's not a vector space. Actually, it has may have a ring structure, but it's not a vector space because it's not closed with respect to scalar multiplication. So under addition, it's closed. Under addition, it is closed. So let's prove these three properties first. Proof. So f is an upper function, g is an upper function, so both must have generating sequences. So let's take their generating sequence. Let phi n and psi n be the generating sequences for f and g respectively. Okay, then this phi n, it increases to f almost everywhere, and this limit n approaches to infinity, integral of psi n is finite. And one more thing, this psi n, it will increase to g almost everywhere. The second property is limit of the integral of psi n is finite. Now this one, now you can see this phi n plus psi n, it increases to f plus g almost everywhere. So we'll see that this sum is generating sequence for f plus g. So that will give f plus g is an upper function. Okay. First we verify that this f plus g is an upper function. Then we try to find the integrals are equal actually here. F plus g. So next we show that this limit of phi n plus psi n integral, limit of the integral of phi n plus psi n is finite, and this limit of integral of phi n plus psi n. But integral of phi n plus psi n for step functions, it is already done. It's equal to integral of phi n plus integral of psi n. So it is equal to limit of integral of phi n plus limit of integral of psi n. Okay. And both the limits exist because both are finite. Here you can see, and therefore the limit of when we have a two sequence a n and b n, so that the limits of both exist. Limits of the both sequences exist. Then the limit of a n plus b n is equal to limit of a n plus limit of b n. So here we have limit of integral of phi, it exists. Limit of integral of sin, it exists. So therefore limit of integral of phi psi n plus, actually it's first here, it's this limit is not here. Okay. So it's the limit of this. Okay. Limit of this. Now we can separate the limits because both the limits exist. It's equal to limit of integral of phi n plus limit of integral, because both are finite, therefore we can separate the limits, and both are finite. This is good. This is finite. So first we have applied the property of this integral of step function. Integral of phi plus psi is equal to integral of phi plus integral of psi. Then we have applied the property of the limits because both the limits are finite. So the limit, we can separate these two limits. So that means the limit of the integral of phi plus psi is less than, is finite. So therefore Therefore, phi n plus psi n is a generating sequence. Is a generating sequence for f plus g, and thus f plus g is an upper function. F plus g is an upper function. Is an upper function. Now we try to find, and now we try to show that this is integral of f plus g is equal to integral of f plus integral of g. Now integral of f plus g, by definition, it's equal to limit n approach to infinity integral of phi n plus psi n, because phi n plus psi n is the generating sequence for f plus g. Now we can separate the limits as in the earlier case, as we have seen this. This is equal to integral of phi n plus limit n approach to infinity integral of psi n. But this one it's equal to integral of f, because this is the generating sequence for f, and this one it's integral of g. So this proves the first property of upper functions. Now the second property, which is obvious actually. So let's choose generating sequence for f, because f is an upper function. Let phi n be a generating sequence for f. Then this phi n, it increases to f almost everywhere, and the limit of integral of phi n is finite. This implies alpha times phi n will also increase to f, because it is also an increasing sequence if alpha is a non-negative. That's why it should be non-negative for this. Actually, it's almost everywhere, and the limit of integral of alpha phi n, which is equal to alpha times, this is done in the step function actually, alpha times limit of integral of phi n, which is finite. Okay, where this alpha is greater or equal to 0, this alpha should be greater or equal to 0, where alpha is greater or equal to 0. So alpha cannot be negative, because otherwise this will not be an increasing sequence here. So this implies alpha phi n is a generating sequence. This implies alpha phi n is a generating sequence for it's a generating sequence for alpha f. So thus alpha f is an upper function. Thus alpha f is an upper function where this alpha is greater or equal to 0. Now we try to prove this equality of integral. This is equal to limit n approach to infinity integral alpha phi n, because alpha phi n is generating sequence, and this is equal to alpha times limit n approach to infinity integral of phi n, and which is equal to alpha times integral of f, because alpha n is generating sequence for f. That proves the second property. Now we prove this last property. Third property. Now let again we assume let phi n and psi n be generating sequences for f and g. Then we know that those two properties are there. So let's take these are generating sequences. Then also I will write those properties here. Okay. Then phi n increases to f almost everywhere, and limit of integral of phi n is finite. And the one more property for G now, cyan increases to G almost everywhere, and limit of integral of cyan is finite. This implies, let's take the join now. Let's take the join of phi and cyan. This will increase to f join G. So limit of phi and cyan is and this join of these join of step functions is again a step function. So therefore phi and join cyan is a sequence of step functions, and it increases to f join G. We need to show that f join G is a generating sequence. So for this we have to find the generating sequence for this function. So we'll see that this is the generating sequence actually. This one, so not I will not here join. I will use here meet first. Then I will do the result for join. Okay. So there's a reason for this why I'm taking first meet. So meet these two functions. Okay. Meet. This will also increase to f plus g. Okay. So we show that this is the generating sequence for f meet g. Okay. So for this we need to show the integral of phi n meet cyan should be equal to finite. Limit of the integral of phi n meet cyan should be finite. Now let's try to prove that. So for this we have this. We have the phi n meet cyan. It's less or equal to phi n as well as cyan. So I will write phi n less or equal to phi. So this is a step function. This is a step function, and there is lesser equality between these two. So and we know that in the lecture on the step function is where we have seen that whenever we have two step functions phi and psi with phi less or equal to psi, then integral of phi is less or equal to integral of psi. So here we have a step function is phi and meet psi and the step function phi. So this implies limit of integral of phi and meet cyan should be less or equal to limit of integral of phi. Actually, this integral of phi and meet cyan is less or equal to integral of cyan. Then we take the limits. But this one is finite because it is a generating sequence for f. So that means this limit is also finite. So therefore, phi and meet cyan is a generating sequence. Is a generating sequence for what? For f meet t, and thus f meet g is an upper function. Is an upper function. Also, what's its integral? Also integral of f meet g is equal to limit and approach to infinity integral of phi and meet cyan. Okay. Now we try to prove this. The join is also an upper function. So now this. Now you can see this phi and join cyan. It increases to f join g. So here I want to mention that why I have taken first meet, because of this reason, because join is not less or equal to phi and cyan. So I have first taken the meet, and I know that this meet is less or equal to phi. Then I have applied this that this phi is a generating sequence for f. So this integral is finite. Therefore, this limit of this integral is also finite. That's why I have first taken the meet. Okay, it's the reason. So now look at this. This limit is equal to f meet g. So we try to prove this is the generating sequence for f meet g, which will prove that this f join g. Sorry, which will prove that this f join g is an upper function. So for this we have following identity. We have this identity. This phi and join cyan it's equal to phi n plus psi n minus phi n meet psi n. So what's the integral now? Now let's apply the integral on both sides. So they are all step functions. So we can separate the integrals which we already done. This is equal to integral of phi n plus integral of psi n minus integral of phi n meet psi n. Now let's apply the limit. This limit is finite. This limit is finite. This is also finite. So this implies limit of phi n join psi n. It's equal to these limits. Limit of integral of phi n. Okay. Limit of integral of phi n plus limit of integral of psi n minus limit of integral of phi n meet psi n. And all are finite, therefore this is less than infinity. This is finite. This is finite. So this means that this integral, this limit of the integral of phi n join psi n is finite, and the limit of this we can see is f join g. Its integral is finite. Limit of the integral is finite. So therefore phi n join psi n is a generating sequence, is a generating sequence for f join g, and hence f join g is an upper function, Also, what's the integral? Also integral. It's integral of f join g is equal to limit of the integral of phi n join psi. So that proves all the three properties of upper functions. So the collection of all upper functions will be denoted by cursive u. The collection. So that proves that was the end of the theorem. The collection of all upper functions. The collection of all upper functions will be denoted by this. It is cursive u. This cursive u. Okay. The collection of all upper functions will be denoted by cursive u. Okay. Cursive u is the collection of all upper functions. So next theorem, which is very simple, which is if f and g are upper functions, if f and g are upper functions, if f and g are upper functions such that this f is greater or equal to g almost everywhere, then this integral of f is greater or equal to integral of g. Okay. In particular, it shows that if f is greater or equal to 0 almost everywhere, then integral of f is greater or equal to 0. Because in that case f is an upper function, 0 is also an upper function, therefore integral of f will be greater or equal to integral of z, which is 0. Integral of a 0 function is 0, but you can easily verify. So now let's try to prove this theorem, it's actually very simple. Again, we have to take two step functions. So you can have two step functions for f and g. So let's take this. Let phi n and psi n be generating sequences for f and g respectively. Okay, let's take these two generating sequences. Then you can see then phi n mid psi n, it will increase to f mid g almost everywhere, but f mid g, because f is less or equal to g, so it's equal to f almost everywhere. Okay, and the limit and one more thing, and this also holds, and this is already done in the previous theorem, and limit and approach to infinity, integral of phi n psi n is finite. So therefore this sequence phi n made psi n is is the generating sequence, is the generating sequence for f, but phi n is also the generating sequence for f. Therefore it has two generating sequences, and the integral is independent of the choice of generating sequence. So we have the following. So now let's see this integral of f. Its generating sequence is phi, so its limit and approach to infinity, integral of phi n, which is always greater or equal to, greater or equal to. So sorry, I have to choose here. This is the f mid g. F is less or equal to g. Is f less or equal to g, or f is greater or equal to, sorry, f is greater or equal to g. So this is here f is greater or equal to g. So this is here g. This is here g. The minimum is g. So this means this and this. Therefore, phi is a generating sequence for g. Is the generating sequence for g, not for f. Okay, it's a generating sequence for g here, not for f. Generating sequence for g. Now integral of f, which is equal to this, which is always greater or equal to limit and approach to infinity, integral of phi n mid psi n. But this phi n mid psi n, it's the generating sequence for g, so it's integral of g. So that means integral of f is greater or equal to integral of g. Integral of f is greater. That's what we need to prove actually. Integral of f is greater or equal to integral of g. So this implies integral of f is greater or equal to integral of g. So hence the theorem follows as required, as required. So this completes the proof of this theorem. So in the next lecture, we'll see some more properties of upper functions. So today we will end this lecture with this theorem. Thank you.